So for my warm-up problem here, I've asked us to evaluate this. So the first thing I'm going to do, walk up to the integral, and I realize it's only algebra. So my hope is that there's some way that I can rewrite this to look like x is raised to powers. And the only real thing I can do is to take that square root and to think about that as 1 minus x squared to the 1/2 dx. That's it, I'm stuck. I can't like 1/2 it out. So now my next line of defense is to think, hey, is the derivative of one part equal to the other part so that we can do a u substitution? Well, there's really only two parts here. I've got an x out in front, and I've got that 1 minus x squared inside. So in terms of derivative of one part being equal to the other part, kind of, sort of, if I take the 1 minus x squared as my u. I had a student in office hours the other day who pointed out that usually what we're going to let u is the part that is stuck somewhere. So in this case, the thing that's stuck is all of that stuff underneath the square root. There's nothing else I can do to it. So I'm going to let u be equal to the part that's stuck. Now, u is 1 minus x squared. Then I know that my du is negative 2x dx. I don't have that negative 2 part, but I've got the x and the dx, which means negative 1/2 of du is equal to x dx. Sorry, I usually change colors when I do the u substitutions. I forgot today. We'll just keep going in black. Next thing that I'm going to have to do, because it's a definite integral, I know that I'm going to need to swap my limits of integration. So I'm going to come off to the side. I've got my x values and my u values, and x is going from 0 to 1. So when I plug in 0 for x right here, I've got 1 minus 0 squared, or 1. When I plug in 1, 1 squared is 1, 1 minus 1 is 0. And I know that I mentioned this another time, but when we are rewriting the limits of integration for a definite integral, we have to make sure to keep the pieces in the same place. So when I rewrite this, because the 0 is that lower limit, that's going to make the 1 my lower limit. Since 1 is the upper limit on the x as in the original problem, I'm going to have to put the 0 as the upper limit. Now that x dx, that's what's going to become negative 1/2 du. And that 1 minus x squared, that whole thing we're calling u, which makes this u to the 1/2. We have a couple of choices at this point. I usually put that constant out in front. So that would look like negative 1/2 times the integral from 1 to 0 of u to the 1/2 du. Another choice that we can make, we don't have to do this step, but we can. If it bothers you that the 1's on the bottom and the 0's on the top, and we think about usually that lower bound being the smaller number, we can swap these and make the whole thing negative. And that's one of those properties of integrals like back in 5.2. So this, I could choose to rewrite as positive 1/2 from 0 to 1. That's an option. Either way, I need to find the antiderivative of u to the 1/2, meaning I need to add 1 to the exponent and divide by the new exponent. So I've got that 1/2 u to the 3/2, and then that's going to be divided by 3/2. And we're going from 0 to 1. Because we changed our limits of integration, we aren't going back to x values. We're just going to keep going with this. So when I divide by 3/2, that's the same thing as multiplying by 2/3. which means those 2's are going to cancel out, and I'm going to be left with 1/3 u to the 3/2, and we're going from 0 to 1. So now when I plug in the 1 and plug in the 0, I've got 1/3 of 1 to the 3/2 minus 1/3 of 0 to the 3/2. 1 raised to any power is 1, so I think my final answer is 1/3. Okay, here's my integral. I've got x cubed times natural log of x dx. We're going from e to 4. I walk up to that integral, and I say it's a mixture of algebra and logs. Since it's a mixture problem, I'm hoping for a u substitution, which would mean that the derivative of one part would need to be equal to the other part. Well, the derivative of x cubed is 3x squared, not helping me. Derivative of ln of x is 1 over x, also not helping me, which means we're stuck with integration by parts. I'm going to follow that rule of late, logs, algebra, trig, exponentials, to choose which portion of this I'm going to make equal to u. Since L comes first in the word late, I'm going to make my u equal to the natural log of x. That makes everything else dv, so dv would have to be the x cubed and the dx part. In order to use my ultraviolet voodoo formula, I know that I need the derivative of u, so du is going to be 1 over x dx, and I need the antiderivative of dv so that I can get v back. Since I'm looking at an x cubed, I know I can add 1 to the exponent and divide by the new exponent, which I could write either as x to the 4th over 4 or 1/4 x to the 4th. Plugging all of that into our equation, my u is ln of x, so I'm looking at natural log of x. V was 1/4 x to the 4th. We're subtracting from that the integral of v du. So 1/4 x to the 4th times 1 over x dx. And here I'm going to pause for a second. Because we have limits of integration, notation-wise, that needs to carry through with us to this step. Unlike a u substitution, right, when we make that u substitution, the integral no longer has x's in it on a u sub. It now has only u's. But when we do integration by parts, our integral is still with respect to x, which means I'm not changing what these boundaries are because these boundaries are in reference to x. So I'm going to keep those same boundaries because we are still in reference to x. There is a thing that we have to take care of though, which is this front part. And because it's a definite integral, this is part of our formula, but this also needs to be evaluated from e to 4. We're not going to need to find an antiderivative over here, which is why I've got that vertical line and the numbers at the right-hand edge instead of an integration symbol with the limits on the left-hand side. So let's keep going. Anytime I'm doing integration by parts, I pause at this step so that I can simplify this as much as possible. Well, that 1/4 I can bring out in front. And then x to the 4th times 1 over x, I can cancel one of those x's out to be left with x cubed dx. Nothing has changed over here. If we want, we can put the 1/4 x to the 4th out in front. I don't know why that's mathematically conventional, but it is. I think it's just so that there isn't any confusion about what is inside of the natural log of x. And then we'll put in those limits. So here we're still going from e to 4 and still going from e to 4. Next step, I'm going to need to take the antiderivative here. I don't have a ton of space on the paper, my very large whiteboard paper. So I'm going to squeeze this and put that E right there, because I think I can still fit this. Since I've got x raised to a power, I'm going to add 1 to the exponent and divide by the new exponent. So when I add 1 to the exponent, I'll have x to the 4th. Dividing by 4, but I've already got that 1/4 out there, means I'm going to end up with x to the 4th divided by 16. We still have all of that, so I've got my 1/4 x to the 4th ln of x. And now that everything has been integrated, I can do a single vertical line and show that we're going from e to 4. I'm going to plug in the 4 everywhere and subtract off plugging in the e everywhere. If I plug in the 4, I'm going to simplify the numbers as we go, I think. Question about whether we need a plus c. So I don't ever need a plus c when we have a definite integral. So if I have numbers to plug in, we're not going to write that plus c. We're only going to write the plus c when it's an indefinite integral and we don't have the numbers to plug in. Plugging in here, if I put in 4, well, I don't actually need 4 to the 4th because one of those 4s is going to cancel, and 4 cubed is 64. So I've got 64 ln of 4 minus, and here, if I'm plugging in a 4 to the 4th, 256 divided by 16, I'm back to 16. And then I'm subtracting off plugging in e. Well, there's not much we can do with the e. I'm going to have 1/4 of e to the 4th. When I plug in the e to natural log of x, ln of e is equal to 1. And e to the 4th over 16. And I would walk away and call that my final answer. Getting a population of bacteria. At the beginning, we're told that there are 10 bacteria. So we weren't really given letters for anything. I'm going to let n be, or n of t, be the number of bacteria at time t. So when we're told that there are 10 bacteria in the beginning, that tells me that n of 0 should be 10. Now, we're told that the growth rate of the population after t minutes. So if we're talking about growth rate and thinking about our words from 17a, growth rate means a derivative. So my growth rate for n is going to be dn dt. And we're told that that growth rate is equal to e to the 0.5 t. And then we're asked to find the number of bacteria. Well, if this is my growth rate, 17b, we're all about undoing derivatives. How am I going to undo that derivative? I'm going to take an integral of both sides. So I know that n is going to look like the integral of e to the 0.5 t dt. Since we've all checked out page 345 and memorized all of those antiderivatives, I know that the antiderivative of e to a number times t is going to be 1 over that number times e to the number, oh, sorry, got my decimal point in the wrong place there, 0.5 t plus some constant. Dividing by 1/2 is actually the same thing as multiplying by 2. So I'm going to choose to write this as 2 e to the 0.5 t plus a constant. We've been given this initial condition, which should be enough to solve for that constant. I know that when we plug in 0 for t, our n value is supposed to be 10. So I know 10 should be equal to 2 e to the 0 plus a constant. and e to the 0 is 1. That constant has to be 8. So my number of bacteria after t minutes should be 2e to the 0.5t plus 8. Now that doesn't yet answer the question because we were actually asked to find the number of bacteria after an hour. So my number of bacteria after 1 hour, and here we want to be really careful because it says that t is in minutes. So if t is in minutes, then the number of bacteria after 1 hour means I'm looking for n of 60. So that would be 2 times e, a half of 60 is 30, plus 8. And that's how I would leave the answer, since we're not going to use a calculator. If I look at this, it's just algebra. So my initial reaction would be to hope that I can write this as x's raised to powers. Very similarly to our warm-up problem today, I can't really go any further than this. I'm stuck. My next line of defense is to think about a u substitution. Well, normally, I'm going to make my u substitution based on thinking about, does the derivative of one part equal the other part? In this case, that question doesn't exactly help us. So the derivative of 1 minus x is negative dx, and the derivative of x is dx. So neither of one of those can replace the other. However, I do have a dx out here. So there is a way to rewrite this. And what I'm going to do is to think about the part that is stuck, the part that is stuck inside of the square root. Or u stands for ugly. What's the ugliest part of this? That's square root. If I make u 1 minus x, then du is negative dx. So that's going to take care of this piece. That's going to become u to the 1/2. And my dx is going to become, my dx is going to become negative du. But we won't have translated the x yet. This is sometimes called a back substitution, where I need to go back to what u equals and solve this equation to get the x by itself. Well, if u is equal to 1 minus x, then I can add x to both sides and have u plus x is equal to 1 and get the x by itself by subtracting u. So x is equal to 1 minus u. I'm going to come in here and fill in the 1 minus u. You might look at that and say, it doesn't look any better than where we started, but it is. The difference between this version and this version is now that it's written like this, the part that's in parentheses doesn't have an exponent anymore. So I can distribute that u to the 1/2. And I'm going to take that minus sign and pull it all the way out in front. And then I can distribute the u to the 1/2 to end up with u to the 1/2 minus u times u to the 1/2. There's an invisible exponent of 1. So when I add those two exponents, I'll have u to the 3/2. Each of those, I can add 1 to the exponent and divide by the new exponent. So I'm going to end up with a negative. When I add 1 to the exponent, I'll have u to the 3/2. And then over 3/2. Add 1 to the exponent here, I'll have u to the 5/2 divided by 5/2. And that all important plus c. Don't do all of that work and then give up points. This was an indefinite integral. We did a whole bunch of work, but don't quit yet because we need to take this back to write it in terms of x's. So I'm going to do a couple of things at once. I know that dividing by a fraction is the same as multiplying by its reciprocal, and I'm going to distribute that minus sign in. So this is going to become negative 2/3 u was 1 minus x. So 1 minus x to the 3/2. Minus a minus will make that plus. The reciprocal here is going to be 2/5. And then I've got 1 minus x to the 5/2 plus a constant. For dx. But our instructions are to compute the integral by interpreting it as signed area. Okay, and I just got the question from that we will do next. Sure. So if I'm going to interpret this as signed area, I really need to have a picture. If y is equal to the absolute value of x minus 4, well, I know that that graph is going to look like a V, and the point of that V is going to be at 4. And it's kind of going to look like that. And we are asked to find the area from 0 to 10. Well, all of this is above the axis, so I don't have to worry about signs. This should be positive and this should be positive. I just have to find the areas of each of those triangles. When x equals 0, y of 0, 0 minus 4 is -4, absolute value would make that positive. So that means that this triangle has a base of 4 and a height of 4. So this area is going to be 1/2 that base times that height. This triangle over here, from 4 to 10, that's a base of 6. And now I need to come up with the height. Well, when I plug in 10, 10 minus 4 is 6. So that means this y value up here is 6. So this triangle has an area of 1/2 6 times 6. And when we add those two areas up, we'll get the answer to the integral. So this should be equal to 1/2 of 16 plus 1/2 of 36. We can go further. 1/2 of 16 is 8. 1/2 of 36 is 18. Then I get 24 for an answer there. Pretty similar to one we did a half an hour ago. So I know that I'm looking at integration by parts because I have a mixture of algebra and logs, but the derivative of one part does not equal the other part. Derivative of w squared is 2w. I don't have an extra w in here. Derivative of ln of w is 1 over w. I don't have an extra 1 over w in here. So we're going to need to integrate by parts. L comes first in the word late, which means u is going to become natural log of w. Everything else is going to have to be dv. When I take the derivative of natural log of w, I get 1 over w dw. And when I take the antiderivative of w squared to get v, I'll have 1/3 w cubed. Putting that together, I've got my ultraviolet voodoo. So u times v. And just because I know before I ran out of space, I'm not going to give up all that board space. So u times v, I'm going to have ln of w times 1/3 w cubed minus the integral of v du. So I'll have 1/3 w cubed times 1 over w dw. Notation-wise, we started off with a definite integral, so that notation needs to come along with us. This piece is not something that needs to be integrated again. So this, we're gonna put that vertical line and the 1, 2 on there because it's ready to just plug in the 2 and subtract off plugging in the 1. This piece over here, we still need to integrate. So we're gonna put the 1 and the 2 on the integration symbol. My next step, anytime I'm doing integration with parts, is to simplify before I find an antiderivative. So here I'm gonna choose to write this as 1/3 W cubed ln of W. Here, I'm going to take that 1/3 out in front, and the W cubed times 1 over W, one of those W's will cancel out, and I'll be down to W squared dW. Again, I want to make sure that I bring those limits of integration along with us. So I've got 1 to 2 and 1 to 2. Next up, we need to find the antiderivative over here. So when I add 1 to the exponent, I'll have W cubed. Dividing by that new exponent means dividing by another 3. So I'm going to have W cubed divided by 9. Over here, I still got that 1/3 W cubed ln of W. And because at this point, we've integrated, we've found all the antiderivatives we need to, I could put the whole thing with a single bar at the back going from 1 to 2. And then our last step is going to be to plug in the 2 and the 1. Well, when I plug in 2, 2 cubed is 8. So I've got 8/3 ln of 2 minus, when I plug in the 2 here, I'll have 8 over 9. So 8/9. And then we're going to subtract off plugging in the 1. Well, 1 cubed is 1, so I've got 1/3, but natural log of 1 is 0. So that's going to be 1/3 times 0 minus, when I plug in the 1 here, I'm going to get 1/9. And then there are a few different ways that we might go about cleaning that up. So for example, there's not much I'm going to do with the 8/3 ln of 2, short of putting that into a calculator or something. But I'll go ahead and leave that 8/3 natural log of 2 alone. But I do have negative 8/9, and when I distribute this minus sign in, that's going to be plus 1 more 9th. So I'm going to have 8/9 plus 1/9. Oh, I lied. It's negative 8/9. Negative 8/9. Distribute that minus sign in, plus 1/9. Yeah, that doesn't get a whole lot better. You could call that minus 7/9. But I think that's the best we're going to do without a calculator.